Wave propagation, space waves, part 2, series on antennas and wave propagation, lecture number 6.18. This is second part, second session of the presentation on space waves. In this part, the focus is going to be on horizons, optical horizon and radio horizon, space wave link range, polarization, ducting, and at the end, we spare a few moments for troposcatter communication too. We begin the session with a discussion on horizon. The term horizon usually refers to the line in the far distance where the sky appears to meet the land or the sea. It holds the same meaning in space wave communications too. In the study of space wave communication systems, we come across two types of horizons. These two are highly related to each other. One is visible horizon, another is radio horizon. A few points regarding visible horizon. True horizon is the line that separates Earth from the sky. True horizon, based on geometric straight line of sight, is given by this formula. D is 3.566 into 10 power 3 square root of HE. Here HE is height of the eye, human eye. D is true horizon, distance of true horizon. D and HE both are in meters in this formula. At many locations, trees, buildings, mountains, etc. obscure the true horizon. The resulting intersection of earth and sky is called visible horizon. True horizon, visible horizon. True horizon is the one in the absence of any obstructions. Visible horizon is the one in the presence of obstructions like trees, buildings, mountains. A few points regarding radio horizon. It is the locus of points of which direct rays from an antenna are tangential to the surface of the earth. If the earth was a perfect sphere and there were no atmospheric anomalies, the radio horizon would be a circle with radius which is same as that of true horizon. So radio horizon is a true horizon when there were no atmospheric anomalies and if the earth was a perfect sphere, means trees, buildings, etc. are absent. Before going further, one or two points which differentiate optical horizon from radio horizon. Optical horizon is the one that is seen by human eye, whereas a radio horizon is the horizon that is visible to antenna. Optical horizon is light based, whereas the radio horizon is radio wave based. We are going to see radio horizon is going to be larger than optical horizon. It is because of bending of the radio waves towards the earth by atmosphere. Now let us move further. VHF and UHF radio signals bend slightly towards the Earth's surface. The curvature of the ray paths by the atmosphere causes the radio horizon to differ from optical horizon. The distance from an antenna to the radio horizon in miles is square root of 1.5 kHa. Here HA is height of the antenna in feet and for standard atmosphere K value is 1.33. In case of standard atmosphere, as K is 1.33, radio horizon distance in miles, it becomes square root of to HA. And in kilometers, it can be converted into kilometers. It becomes 4.266 into 10 power 3 square root of HA. Here HA, height of the antenna, is in meters. The significance of radio horizon lies in the fact that maximum possible distance, called a line of sight distance, at which direct ray transmission is possible between transmitter and receiver antennas of given heights, is equal to sum of the horizon distances calculated separately for the individual antenna heights. Now, what is optical horizon? This is here. You are here. Your eye is here. You can see only up to this point. This distance is optical horizon. Beyond this distance, optical horizon, our eye cannot see, because from this point onwards, if you look downwards, it is earth. If you look upwards, it is a sky. Now, what is radio horizon? Let us suppose this is antenna tower. Antenna is here. Because of bending of the radio waves, what happens is waves travel like this, like this, like this, like this, like this, like this, and they may reach points which are far away than the optical horizon distance. Far away points located on the earth. The distance up to which the radio waves can reach is radio horizon. Now, space wave link. Here is depicted a space wave link. This is Earth's surface, transmitting antenna, receiving antenna. This is D1, this is D2. The link range is D1 plus D2. Dmax, maximum distance of the link range, maximum link range is D1 plus D2. It is nearly square root of 2A HT plus square root of 2A HR. What is A? A is Earth's radius. It is taken as a 6.37 into 10 power 6. Substitution and a little bit of manipulation gives Dmax, maximum link range, as 4 into 10 power 3 multiplied by square root of HT plus square root of HR meters. By increasing the height of the transmitter and the receiver antennas, the transmission range can be increased. For typical antenna heights of 150 meters, the range is 100 kilometers approximately. This derivation is based on optical horizon. The space wave slightly gets bent towards the earth, and as a result, radio horizon is slightly more than optical one. If it is taken into account, range becomes more than 100 kilometers. This D1 is optical horizon. D2 is optical horizon. D1 is square root of 2A HT. D2 is square root of 2A HR. If we consider radio horizon, it is going to be more than 100 kilometers. Link range can be more than 100 kilometers, maybe 125 kilometers or so. Another aspect, field at the receiver of a link, space wave link. Here earth is assumed to be flat. This is the height of transmitting antenna. This is the height of receiving antenna. At the receiving antenna, one can see there are two rays. One is direct ray, another is ground reflected ray. The distance traveled by direct ray to reach the receiver is R1, whereas distance traveled by reflected ray to reach the receiver is indicated by R2. D is the distance between the antennas. It is link range. When reflected ray is included in the calculation, electric field intensity at the receiver can be found equal to 4 pi HT HR over lambda d square, square root of P eta naught by 4 pi. When reflected ray is suppressed, the field intensity at the receiver can be found equal to square root of P eta naught GT over 4 pi 1 over D. Compare these two relations. When reflected ray is there, E is inversely proportional to distance square. In the absence of reflected ray, E is inversely proportional to distance. So field intensity falls very fast when reflected ray is there in the functioning of the link. In the absence of the reflected ray, the fall in field intensity with the distance is not that much. Therefore, reflected ray is unwanted. Its presence is unwanted. It requires to be suppressed. In these expressions, the symbols carry their usual meanings. HT, HR are heights of antennas, D is distance, lambda is wavelength, P is transmitted power, eta naught is intrinsic impedance of the medium, GT is gain of the transmitting antenna. All carry their usual meanings. A few points of explanation. At large distances, in the presence of reflected ray, the field strength varies as 1 by d square and consequently decreases much rapidly with the distance. In the absence of reflected wave, field varies as 1 by d and consequently decreases less rapidly with the distance. Hence, reflected ray requires to be suppressed. To reduce the presence of reflected wave, directional antennas are used. Directional antennas are used not only for better line of sight focusing, but also to suppress the reflected wave, thereby giving higher transmitting range. Some more points regarding a field at receiver. When the curved surface of Earth is taken into account, certain modifications to the results obtained assuming flat Earth are to be made. Whatever expressions that are given in the previous slide, they are derived assuming flat Earth. But Earth is not flat, it is curved. When that aspect is taken into account, how the relations given earlier are going to be modified. The location and the number of maxima and minima of a flat Earth field strength curve change. This is aspect. It also reduces the distance beyond which the two rays tend to be out of phase. The ground reflected wave becomes diverging rather than plane wave, resulting in a weaker reflected wave at the receiver. So, curved Earth's surface, it does good in this aspect. It weakens the reflected wave at the receiver. Thus, for a given height of transmitter receiver tau, there is an upper limit on the distance over which there is a line of sight between transmitter and receiver. The angle between the direct wave and reflected wave becomes less, making it difficult to suppress the reflected wave using directional antenna. So these four are points which explain the impact of a curved surface on a space wave communication link. Out of the four, second one is something which explains positive aspect, positive result of Earth's surface. Third one says curved surface of Earth means distance over which line of sight conditions prevail. It gets limited by curved surface of the Earth. So it is negative aspect. Last one says another negative aspect. Even directional antennas are also unable to suppress the reflected wave completely. Now we move to another area aspect, an important aspect pertaining to space wave communication links. It has been seen earlier, the link range is usually 100 to 150 kilometer. It is less than 150 kilometer. But sometimes when certain conditions are satisfied by the atmosphere, troposphere, the link range gets enhanced in an abnormal manner. The link starts working satisfactorily even when the distance between antennas is more than 1000 kilometers. It is found the reason for this functioning is a phenomena called ducting. We discuss about it here in depth. The phenomena ducting is also known as trapping propagation or super refraction. These are different names. Ducting, trapping propagation, super refraction. Ducting is useful in extending the range of microwave communication link. Due to this phenomena, wave can travel even more than 1000 kilometers. The main requirement for the formation of duct is temperature inversion. Increase in temperature with height. This is the requirement, main requirement. As a result, energy originating in the region and initially directed approximately parallel to the ground tends to be trapped and propagate around the curved surface of the earth in a series of hops involving successive earth reflections. Going further, before that, a few words regarding understanding of ducting phenomena. Ducting is a atmospheric phenomena. It occurs in troposphere. This phenomena involves formation of a tubular or hollow atmospheric structure near the surface of the earth like this. When signal enters into this pipe, atmospheric pipe, it then travels large distances by means of reflections from the surface of the earth and by means of bending from upper portions of the atmosphere, upper parts of the duct like this. Hence, the signal is trapped in the duct. After getting trapped, it travels by multiple reflections to far away distances. The distance can be more than 1000 kilometers. For duct formation, requirement is temperature inversion. Now, let us move further. More understanding regarding ducting phenomena. Under ducting conditions, trapped or guided wave travels along the duct much as a wave is guided by a leaky waveguide. Ducting occurs when the moisture content of the air at the surface of the ground is very high but decreases rapidly with increase in height. In this region, the ratio dm by dh. M is modified refractive index of the atmosphere. Troposphere, H is height. dm by dh becomes negative. Curvature of rays passing through the atmosphere is greater than that of the earth. The receiving antenna must be elevated to be within the duct to have large signal strength. If the receiving antenna is outside the duct, either above or below, signal strength becomes very low. To use duct formation for communication purpose, what we have to do is we have to see that the receiving antenna is in the duct. Then only it can be able to receive the signal that is there in the duct. Otherwise, signal strength at the receiver becomes low. Here is the explained ducting phenomena in diagrams. In A is shown standard atmospheric conditions. A describes variation of M with height h. M stands for modified refractive index, height above surface of the earth. There is a curve, its slope is 0.03 units per foot. In B is shown variation of M with height when refraction at lower heights equals Earth's curvature. Up to certain height, M assumes constant value, fixed value. After that, M starts increasing with height. In C is shown simple surface duct. There are two types of ducts, surface duct and elevated duct. Surface duct means the lower part of the duct is over the surface of the air. That is surface duct. This is surface duct. Elevated duct means the duct total thing is at a height above the surface of the earth. In C is shown variation of M with height in case of surface duct. M decreases with height up to certain height. After that, it starts increasing. This is the surface duct. In D is shown elevated duct. In this case, M usually starts increasing with height up to certain point. After that, it decreases up to certain height, and after that it starts again increasing. The duct region is shown clearly in this diagram. In C is also shown, the duct portion is indicated. Ducting continued. Surface duct. If the lower side of the duct is at the surface of the earth, it is called surface duct. In trade wind belt over sea areas, there appears to be a continuous surface duct about 5 feet thick. Over land areas, they occur due to the radiation cooling of the elevated duct. If the lower side of the duct is at an elevation, at a height, then it is called elevated duct. Elevated ducts are due to subsidence of large air masses and found at elevations of 1000 to 5000 feet, with the thickness varying from a very few feet to 1000 feet. Now, angular range. The energy represented by the rays within the angular range of 1 degree or less above the horizontal only gets trapped, while rays falling outside this range ultimately pass out of the duct to the space above. What is this point? Here is transmitting antenna. We have to see that most of the radiated power falls within 1 degree from horizontal. Let us say this is 1 degree above, this is 1 degree below horizontal. The power should fall within these 2 degrees surrounding the horizontal. It implies, what it says is, if we want ducting phenomena for extending the range, link range, we have to use the transmitting antenna which exhibits narrow beam widths. So 1 degree or less means narrow beam width transmitting antennas are required to establish the space wave link. Critical frequency. As with the ordinary waveguide propagation, there is a certain critical or threshold frequency which depends on the thickness of the duct below which duct propagation does not occur. Also, the tendency for the energy to leak out of duct increases with the ratio lambda by hd, that is wavelength to duct height ratio. And if this ratio exceeds a certain value, duct effect altogether disappears. Before going further, one point regarding critical frequency. If we want to use duct phenomena for our benefit, we have to see that the frequency, central frequency of the link should be above certain value. That minimum value of frequency is called critical frequency or threshold. This slide is about critical frequency. The maximum wavelength, the lambda max allowed for duct propagation is 2.5 hd multiplied by square root of delta m into 10 power minus 6. Here delta m is total decrease in m from bottom to the top of duct. Lambda max and hd are in same units. For typical values of duct height and m variations, it can be found that duct propagation is ordinarily limited to UHF and microwave frequencies. So below UHF, usually things do not work if you want to use ducting phenomena. A few points regarding polarization. Both linear polarizations, horizontal and vertical, are used in space wave links. For any angle other than grazing or vertical incidence, magnitude of the ground reflected wave will be less with vertical polarization than horizontal polarization. Height below which ground wave action must be taken into account is much less with horizontal polarization than with vertical polarization. As the man-made noise is predominantly vertically polarized, it is possible to achieve some discrimination against these disturbances by employing horizontal polarization. And for this reason, horizontal polarization is being used in television, and FM broadcasting systems. Here things are self-explanatory, self-evident. We move to another area. This area is not totally different from space wave propagation. Here it is called tropospheric scattering. A few points regarding these systems. The phenomena tropospheric scattering is also known as troposcatter or forward scatter propagation. It is one of the means of beyond the horizon propagation for UHF signal. The mechanisms involved appear to be scattering and reflections from the inhomogeneities in the refractive index of the atmosphere within the common volume of the troposphere occupied by transmitting and receiving beams. The received signal is ascribed to scattering from eddies or blobs in the atmosphere due to turbulence or uncorrelated reflections from many layers of limited extent and arbitrary aspect. Here is a described troposcatter propagation. This is a transmitting antenna, this is a receiving antenna. So transmitter is emitting waves like this. Here in the scatterer volume, a part of the incident wave is getting reflected, another part is scattered away. Similarly, lower ray also, a part getting and when there is no scattering, these two rays might have gone like this. But because of scattering, they are redirected towards the receiving antenna. Salient features of tropospheric scattering. One, this is a permanent state of affairs, not a sporadic phenomena. Second, it can provide a consistent and reliable beyond the horizon signal for distances up to 300 to 400 miles. Three, the range of frequencies useful is from 100 to 10,000 megahertz. High gain antennas required, but their size should be restricted to realize its full gain. Beyond the horizon, the received signal power decreases at about seventh or eighth power of the distance. Sixth, there exists fast fading, which is essentially random and follows a Rayleigh distribution. Seventh one, diversity reception is almost essential and requires antennas spaced at least lambda apart. 8, available bandwidth is sufficient to provide a television transmission over a 200-mile link. With this, we come to an end to the second part of presentation on space wave propagation. In this session, the focus is on horizons, radio horizon and optical horizon, link range, field strength, ducting, polarization, and troposcatter phenomena has also been discussed. Hope this session is useful to you. We meet again in another session very soon with a new topic.